Okay, I hope I'm audible to all the students who are attending this lecture. We start with a new topic in statistics today. This is called as point estimation. This is called as point estimation. Okay, so let's look at what is meant by point estimate. So first of all, what we'll be doing in this particular topic is that there will be something called a population parameter, and what we'll be doing is from the sample we will find a statistic which will be used to estimate the population parameter. So I again repeat, our objective is to estimate the population parameter, and to estimate the population parameter we will be using a statistic from the sample. Okay, so let's look at the definition of point estimate. So definition: a point estimate of a parameter theta. This is the population parameter. Theta is the population parameter. So a point estimate of a parameter theta is a single number that can be regarded as a sensible value for theta. Okay, so when we talk about a point estimate of a population parameter theta, it is a single number that can be regarded as a sensible value for theta. Okay, so how is a point estimate obtained? A point estimate is obtained by selecting a suitable statistic. Point estimate is obtained by selecting a suitable statistic and computing its value from the given sample data. So in order to obtain a point estimate, first of all, we will be selecting a suitable statistic. Always remember that a statistic is selected from the sample. A statistic is selected from the sample, and that statistic is used to estimate the population parameter theta. And one particular value of that statistic is called a point estimate. Okay, so we can also write the selected statistic. The selected statistic is called the point estimator of theta. Okay, the selected statistic is called the point estimator of theta and is denoted by theta hat. It is denoted by theta hat. Okay, so I can draw a flow chart to explain it. We have the sample statistic. Sample statistic is a function of the sample values. It is denoted by theta hat and is used to estimate population parameter theta. The sample statistic, which is theta hat, is used to estimate the population parameter, which is theta. And one particular value of theta hat is called the point estimate. So students should not get confused between point estimate and point estimator. Theta hat is a point estimator of theta, but one particular value of theta hat is called the point estimate of theta. Remember students that theta hat itself is a random variable. You take one sample, you get one value of theta hat. You take another sample, you get another value of theta hat, and so on. So theta hat itself is a random variable. Theta hat itself is a random variable. And every random variable has mean and variance. So theta hat, which is a function of the sample values, which will be used to estimate theta. So theta hat will be called the point estimator of theta. And one particular value of theta hat is called the point estimate of theta. So I hope students are clear with this. Some examples of point estimators. For example, suppose we want to estimate the population mean, which is mu. Okay, so what are the estimate, what's the estimator we have for this? So to estimate mu, one point estimator is the sample mean x bar. So I can say that x bar, which is the sample mean, is a point estimator of the population mean. And one particular value of sample mean will be called the point estimate. Okay, some other examples of estimators. Some other examples of estimators. All of us know that we can have various examples. Sample median. Okay, then we can have another estimator, minimum xi plus the maximum value divided by 2. If you take a sample, within the sample, the minimum value plus the maximum value divided by 2, that can also be a possible estimator. All of us have done trimmed mean before. So trimmed mean is also an example of an estimator, and so on. Okay, but the very famous sample estimator which we have done is called the sample mean. The sample mean is used to estimate the population mean. So it's called the point estimator, and one particular value of x bar will be called the point estimate. Okay, so let's move forward. I hope students have understood the underlying theory behind point estimation. Now let's look at the desirable properties of point estimators. So desirable properties of point estimators. So when we look for a point estimator, which is used to estimate the population parameter, what should be the properties it should possess? So first of all, let's write the initial part. Let theta hat be a sample statistic. Let theta hat be a sample statistic being used as a point estimator of an unknown population parameter theta, where my sample statistic theta hat is a function of the sample values x1, x2, ... xn. Okay, so let theta hat be the sample statistic, which is called the point estimator of the unknown population parameter theta. And all of us know that the sample statistic theta hat is a function of x1, x2, dot, 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 xn. Then the first definition for the day, the first property. Theta hat is called a linear estimator. So we are doing the definition of linear estimator. Theta hat is called the linear estimator of the population parameter theta if and only if theta hat is a linear function. Theta hat is a linear function of the sample values x1, x2, dot, 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 xn. So we say that theta hat will be called a linear estimator of theta if and only if theta hat is a linear function of the sample values. Sample values are x1, x2, dot, 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 xn. Then let's look at the example. Okay, so let's look at the examples of linear estimators. Okay, so first of all of us know the sample mean x bar, which is x1 plus x2 plus xn divided by n, is a linear estimator. It is a linear estimator of the population mean mu. Why? Because x bar is a linear function, because x bar is a linear function of the xi's, the sample values. All of us know that what is x bar? X1 plus x2 plus dot, 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 xn divided by n. You can clearly see that x bar is a linear function of the xi's. There is no quadratic, there is no cubic, it's a linear function. Since x bar is a linear function of the sample values xi's, hence it's a linear estimator of the population mean mu. Similarly, if I define to you one estimator, suppose x dash, hypothetically. X dash is what I've taken in my lecture note, 1/3 of x1 minus 2/3 of x2 plus 5/8 of x3. Suppose this is my estimator. Now you can see this is also a linear estimator. This is also a linear estimator because x dash is a linear function of the xi's. X bar is a linear function of the xi's. In this case, x1, x2, and x3. But if I talk about the sample variance, all of us know the sample variance. What's the formula for sample variance? The formula for sample variance is summation xi minus x bar ka square upon n minus 1. All students should know that we divide by n minus 1, not n, because when we talk about sample, we have n minus 1 degrees of freedom. So our sample variance is summation xi minus x bar ka square upon n minus 1. Why do we divide by n minus 1? Students can refer to the first lecture note of statistical methods for economics. In that, when we had taken the example of sample variance, I had specified the reason in the lecture as to why we divide by n minus 1 and not n. So you can see that the sample variance is this, which I can further write as summation a minus b square is a square plus b square minus 2ab upon n minus 1, which is clearly not a linear function. Which is clearly not a linear function of the sample values, that is xi's. Hence, the sample variance is not a linear estimator. It is not a linear estimator of the population variance sigma square. All of us know that the sample variance is used to estimate the population variance. But sample variance is not a linear estimator. Why is it not a linear estimator? Because it is not a linear function of the sample values. You can see that xi's are coming in square terms, xi square. So it's not a linear estimator. So what do we learn from this example? Sample mean is a linear estimator of the population mean because sample mean is a linear function of the xi's. I have taken another example. X dash is also a linear estimator in general because it's a linear function of x1, x2, and x3. But if I talk about sample variance, it is not a linear estimator of population variance because sample variance is not a linear function of the sample values, which is the xi's, since xi's are coming in quadratic terms. Okay. So this was our first definition of linear estimator. Now let's look at the second definition, definition 2. This talks about unbiased estimator. Definition 2 talks about unbiased estimator. So let's write this definition. A point estimator theta hat is said to be an unbiased estimator of theta if and only if expected value of theta hat is equal to theta for every possible value of theta. For every possible value of theta. So we say that theta hat is said to be an unbiased estimator of theta if the expected value of theta hat is exactly equal to theta for every possible value of theta. However, if theta hat is biased, then expected value of theta hat is not equal to theta, and expected value of theta hat minus theta is called the bias of theta hat. It's called the bias of theta hat. So when the point estimator is biased, expected value of theta hat will not be equal to theta, and expected value of theta hat minus theta will be called the bias of theta hat. So I hope all students have understood the definition for unbiased estimator. An estimator theta hat will be called an unbiased estimator if expected value of theta hat is exactly equal to theta, and if in case theta hat is biased, expected value of theta hat will not be equal to theta, and the bias of theta hat will be expected value of theta hat minus theta. Okay. Now let's do some practice questions on unbiased estimator. So our heading now is practice questions on unbiased estimators. So let's look at some of the questions on unbiased estimators. The first question is show that the sample mean x bar is an unbiased estimator of the population mean. show that the sample mean x bar is an unbiased estimator of the population mean mu. Okay, so what do we need to show? We need to show that expected value of x bar is exactly equal to mu. So let's do the proof. Expected value of x bar, I can write expected value of, what is x bar? x1 plus x2, all the sample values divided by n. Now guys, n is a constant, it comes out of the expectation. I can write it like this. Okay, and now expectation of a sum is the sum of expectations. I can write it like this. And all the xi's are independent and identically distributed. They are IIDs. So I can write expected value of x1 is also mu. Expected value of x2 is also mu. And this is also mu. How many times? N times. Why is this? Because xi's are independent and identically distributed. IIDs. All the xi's are independent and identically distributed. So in fact, just to make it more sensible for all the students, let me take it as capital X's only, because they are random variables. So this can be capital X1 plus capital X2 plus capital Xn, because all the xi's are x1 itself is a random variable, x2 itself is a random variable. Okay, so I can write it like this. I'm doing this for more clarity, so it becomes expected value of x1 plus expected value of x2 plus dot 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 expected value of xn, and then I can say that the capital xi's are independent and identically distributed random variables. Since they are independent and identically distributed, expected value of xi is equal to mu. So I can write 1 upon n times, if I add mu n times, I get n mu, n and n cancel, I get mu. So we have shown that expected value of x bar is equal to mu. Hence, x bar is an unbiased estimator of the population mean mu. So I hope all students have understood this, how we have shown that the sample mean x bar is an unbiased estimator of the population mean mu. It was a simple proof. We used the definition. Expected value of x bar is expected value of x1 plus x2 plus dot 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 xn divided by n. N is a constant, comes out of the expectation. Expectation of a sum is the sum of expectations. Expected value of x1, expected value of x2, all of them are equal to mu, because xi's are independent and identically distributed random variables. Okay, and 1 upon n into n times mu gives us mu. Okay, so let's move forward to the next question. Question 2. Show that x dash, which is 1 upon 6 times x1 plus 2 by 3 times x2 plus 1 by 6 times x3 is an unbiased estimator of the population mean mu, but x star, which is 1 by 6 times x1 plus 3 by 5 times x2 minus 1 by 3 times x3, is a biased estimator of the population mean mu, where x1, x2 and x3 are independent and identically distributed random variables. So we need to show this. Okay, so let's go through this once. Let's look at the solution. So consider x dash, which is 1 by 6 x1 plus 2 by 3 x2 plus 1 by 6 x3. We need to show that x dash is an unbiased estimator. So if I do expected value of x dash, its expected value of this term, okay, which I can further write as 1/6 of expected value of x1 plus 2/3 of expected value of x2 plus 1/6 of expected value of x3, which I can write as 1/6 of E of x1 is mu, 2/3 of E of x2 is also mu, 1/6 of E of x3 is also mu. Why are all of them equal to mu? Because x1, x2, x3 are independent and identically distributed random variables. All these three have identical distribution, so their expected values are all equal to mu. Now if I solve this, 6 is the LCM, mu plus 4 mu plus mu, which is 6 mu by 6, which is equal to mu. So we have shown that expected value of x dash is equal to mu. Therefore, x dash is an unbiased estimator of mu. X dash is an unbiased estimator of mu. Then let's look at the second part of this. Let's look at x star now. Okay, so I'm erasing this off. Let's look at x star. So students can do the same analysis for x star as well. Now consider x star, which is 1/6 of x1 plus 3/5 of x2 minus 1/3 of x3. Now if I do expected value of x star, it is expected value of 1/6 of x1 plus 3/5 of x2 minus 1/3 of x3, which I can write like this. I can write it like this. Now again, expected value of x1 is mu, expected value of x2 is also mu, expected value of x3 is also mu. Why? Because xi's are independent and identically distributed random variables. Now if I find this out, my LCM is, I can take 30 as the LCM. So 6 5s are 5, 6 are 6 3s are 18 and 10 mu. So you can see it comes out to be how much? It comes out to be 18 plus 5, which is 23 minus 10. So this is 13 mu by 30. Okay, it comes out as 13 mu by 30, which is not equal to mu. So therefore, expected value of x star is not equal to mu. Therefore, x star is not, or I can say x star is a biased estimator. X star is a biased estimator of mu. And if I ask you what is the degree of bias, if I ask you what is the degree of bias, so degree of bias is equal to 13 mu by 30 minus mu, which is 13 minus 30 is how much? Minus 17 mu by 30. This is the degree of bias. Okay, so I hope students have understood question 2. X dash is an unbiased estimator because expected value of X dash is equal to mu, but X star is a biased estimator because expected value of X star is not equal to mu. And if you want to find the degree of bias, it's 13 mu by 30 minus mu, which is minus 17 mu by 30. So I hope all students are clear with this. And then let's do one more question. Question 3. Prove that when X is a binomial random variable, prove that when X is a binomial random variable with parameters N and P, then the sample proportion P hat, which is equal to X by N, is an unbiased estimator of P, that is the population proportion. So we need to show that if X follows a binomial random variable with parameters N and P, then the sample proportion P hat, which is equal to X by N, will be an unbiased estimator of the population proportion P. So let's look at the proof. Very simple. So we need to show what? We need to show that expected value of P hat is equal to P. So very simple, it's a one-line proof. Expected value of P hat will be expected value of, what is P hat? X by N, sample proportion. P hat is the sample proportion, which is X by N, where N is the sample size. Now guys, N is a constant, comes out of the expectation. All of us know what is the mean of the binomial random variable, NP. All of us know that the mean of the binomial random variable is NP. This comes out to be P. So we have shown that expected value of P hat is equal to P. Therefore, P hat is an unbiased estimator of P. Or I can say that the sample proportion is an unbiased estimator of the population proportion. Okay, and so this is where I stop in this lecture. Okay, one more thing I would want to discuss. One last thing, there's a proposition. Let's discuss this proposition. If x1, x2 to xn is a random sample from a distribution, it can be any distribution with mean mu, then the sample mean x bar is an unbiased estimator of the population mean mu. Also, if in addition the distribution is continuous and symmetric, suppose it's a continuous and a symmetric distribution, then the sample median x tilde, it's the sample median, and the trimmed mean x tilde, which is the trimmed mean, are also unbiased estimators of the population mean mu. So what is this proposition telling us? It is telling us that if x1, x2, xn is a random sample from any distribution, not necessarily normal, it can be any distribution, then the sample mean x bar will be an unbiased estimator of the population mean mu. And in addition to it, if the distribution is a continuous distribution and it's symmetric, then the sample median and the trimmed mean will also be unbiased estimators of the population mean mu. So always remember that under every circumstance, sample mean will always be an unbiased estimator. But sample median and trimmed mean will be unbiased estimators of population mean only if the distribution is continuous and symmetric. Okay, so this is where I stop in the lecture. Homework for all the students. Okay, so show that any convex combination of the sample values x1, x2 to xn is an unbiased estimator of the population mean mu. So I want all students to solve this question at home. We need to show that if we take a convex combination of the sample values, now I give you a hint. Convex combination means that all the coefficients of the xi's should sum up to 1. All students should know about convex combination. All the coefficients of xi should sum up to 1. So we need to show that the convex combination of the sample values is an unbiased estimator of the population mean mu. So I would request students to try this question at home and get back to me. This is where I stop in the lecture. I hope all students have enjoyed the lecture. Any doubt, you can unmute your mics and ask, or call up or mail me your doubts at divineschoolofeconomics@gmail.com. So this is where I stop.